Okay, so I kind of left you behind a little bit, a little technical difficulty. My phone just shut off. I don't know why it shut off, but just shut off. So I have to keep my eye on it to make sure it's recording. All I did was I finished off, okay, this factor that, you know, that if the height of the basic function, parent function is 1, okay, and my value outside of the function is -3 times, then I multiply each y value by -3 times. Notice that the x values don't change. The y values are multiplied by -3. Same thing here, my y value is 2, I triple that, and then I bring it down by reflecting it. That's the negative and the 3. Same thing for the opposite side. I've got a y value of 1, it's tripled, and then brought down to the other side. A y value of 2, it's tripled, and brought down to the other side. So the overall effect that we're starting to see for the number out front here is, it's doing a vertical stretch. Okay, this is a stretch by a factor of 2. This is a stretch by a factor of 3, and it's a reflection. So I describe it. It stays in the same location, so there's no shifting happening, no translations, but it is a vertical stretch. The vertical is downwards rather than upwards, okay? But it's a stretch by a factor of 3, taking all my y values and tripling them, as well as putting a negative in there, which means it flips it upside down and it reflects it. So it's a vertical stretch and a reflection that's vertical, okay, in the x-axis. So the take-home message is looking like this number that's on the outside of the bracket, the outside of the function, is a vertical transformation factor. Okay, now I have this y is equal to 1/2 x. Okay, so I go back to Desmos, not knowing exactly what color it's going to be, and I go y equals, okay, and then I go 1 divided by 2, and it makes it a little 1/2 for me. I may have to scoot 1 second. So I have to get out of the denominator there, okay, and then x, and I don't know how to do that. So there it is. Oops, sorry, it's absolute value of x, my mistake. So let me go backspace. Oops. Oh darn it. Let's do that again. Okay. Y equals 1 divided by 2. I don't know how to cursor out. Maybe that will cursor. Oh, that does cursor out. Okay, good. I know how to do that now. And then x. Okay. X. Okay, and there it is. All right. Now this one's purple. I don't have a purple, so I'm going to have to use green. Okay. But one thing that you'll notice is my black one. That's the base function, right? So my height for y value is 1. What happens to my y value when it's a 1/2 on the outside of the absolute value? Well, it goes from 1 to 1/2. Interesting. Okay. It also goes from, it's normally at 2 here, okay, at x is equal to 2. It's at a y value of equal to 2, but you'll notice it's been halved to 1. And even if we go one step further out, we go to 5, we get 5 units there, it's halved to 2.5. Okay, everything is halved. Every point is halved because the 1/2 is outside of the function there. So it's a vertical, what we call a compression, because I'm kind of pushing down on it. So it's called a compression, if you remember that from last year. I'm going to do this guy in green. And we'll go back up and we'll say, okay, what's going to happen here? Well, at 1, the y value should be 1. Instead, I'm going to make it 1/2. At 2, the y value should be 2. I'm going to make it 1. At 4, the y value should be 4. I'm going to make it 2. I'm halving all of my values. Okay, I'm halving all of my values. Same thing here. A y value of 1, we cut it in half. A y value of 2, we cut it in half. A y value of 3, we cut it in half. A y value of 4, oops, sorry, we cut it in half. Okay, and we draw the other arm of the absolute value function. So this is y is equal to 1/2 absolute x. And I did forget to put y is equal to -3 absolute x. Okay? So hopefully that makes a little bit, okay, a little bit sort of expected. All right, and so again, for the y equals 1/2 x, okay, again, it's going to be, you know, it's going to be the same spot, but it's going to be a vertical, we call it a compression, but it's still times a half. But the half is what compresses it. But either way, I'm taking all the y values and I'm timesing them by a half. So it's a vertical y value halving. There you go. There's no negative in here, so there's no shift or anything like that. Okay? Now, for a function y is equal to f of x, what can you conclude about the translation of y is equal to a f of x? Now remember, a is multiplied by f of x. Okay? And when I say multiplied, it really shouldn't be a times sign, right? It's just the a beside the f of x. When the a is beside the f, it's not adding or subtracting, it's multiplying. So this a thing is our vertical transformation factor. It transforms because it changes the shape, and it's vertical. Now, if my a is greater than 1, if it's 1.1 or 2 or 4 or 6 or 8, it's going to be a vertical stretch by a factor of a. Okay? Or we'll go a times. Okay? If my a value is less than -1, which means it's like the -3, okay? That's also going to be a vertical stretch. So as long as my value is, the number part is bigger than 1, it's going to be a stretch because it's going to multiply by a number bigger than 1 for the y values, which means it's going to stretch it vertically. Okay? But the fact that it's negative, and a reflection in the x-axis, or a vertical reflection. Okay, so it's vertical, vertical, vertical. Okay, vertical means y values. Okay, if my a value is smaller than 1 or bigger than -1, in other words, the number part is smaller than 1. It's between 0 and 1. Okay, so it's a teeny tiny number, like the 1/2 fraction. Okay, it's still going to be a vertical. It's still going to be by a factor of a times. Okay, but what we have to say is it's going to be a compression. So it's not going to get taller or stretch it, it's going to get squished. But it's still vertically taking the y values and doubling or tripling or halving or whatever. Whatever the a value is, it does it to the y values by multiplying. And the nice thing is we're going to leave the a the same way. Okay, now, if it's negative, it also reflects. If it's this one, there's no reflection. So if it's positive, there's no reflection. So it's kind of variable depending on those two situations. But it's definitely going to be compressed. Okay? And that is basically a review for parabola transformations, except it doesn't just happen to the parabola. We did the same thing for our root function, right? And then we did the same thing for our we did the same thing for our root function with our translations. And now we're doing the same thing for our root function, okay? But it doesn't have to be a parabola. It works the same way for every function y equals f of x. No matter what it looks like. It could be some made-up thing. It could be Charlie Brown's zigzag on his shirt. Okay, or it could be some waves that you see in a picture or something like that. Or it could be, I don't know, a happy face. And you put it on an xy axis and you double all the y values. And it looks like this big long happy face when you double it. Okay, it's not as wide, of course. It doesn't look like a circle anymore. Okay, it looks like a stretched circle or an oval. Okay? So let's summarize. Vertical translations. Translations are side to side, up or down, plus or minus. Okay? So vertical translations, okay, they're outside the function. Okay, so they're outside of the square root sign. They're outside of the absolute value function. They're outside of the x squared. Okay? So a function y equals f of x and its translation y is equal to f of x plus c are translations. Okay? If c is greater than 0, I guess translations of each other. Okay? If c is greater than 0, if my c value here on the outside is positive, okay, then y equals f of x plus c is shifted up c units. Okay, if c is less than 0, if c is negative, then it's the same thing. Shifted, the plus c is going to be shifted down c units. It's simple for c. So anything that's added or subtracted on the outside of the function outside of the function, okay, is going to be shifted up or down. Anything that's inside the function, okay, so see, that's the function right there. So it's inside the function, okay, that's inside. Okay, and inside the function means inside the square root sign. At the bottom of the reciprocal fraction. Inside the absolute value. Inside the y equals x squared bracket. If it's inside there, then it's horizontal. Okay? So they are translations. But they are the same image. We use the letter D for this one, not an H and a K anymore. So if D is greater than 0, if my D is it's like a plus 4, okay, then it's going to be shifted this way. Oops, sorry. If D is greater than 0, that means D is positive. Yeah, then it's going to be shifted this way, the opposite of what you expect. Okay? No, you know what? No, I'm not yet. I gotta get this language right. Okay? When it's in the form of the equation, it's a minus d. So when I switch the sign, and once I determine what my d value is, if it's greater than 0, it's shifted to the right d units. So the way that it looks in the equation, it's opposite of what it is. If you see here, it looks like a minus d. Okay? And then it's greater than 0, so it's actually a plus d when we figure it out. It's shifted to the right. If the d value is negative, once you take it out, if this is like x plus d, right, and you take it out and it becomes a negative value, then it's shifted this way, d units. So whatever it looks like in the equation for d, you do the opposite. So it's f at x plus 1, okay, then that's going to be a shift. My d value is going to equal negative 1, and it's going to shift this way 1. Okay? If it's f at x minus 4, my d value is going to equal 4, and it's going to shift this way 4 units. Okay? Probably make that 1, so it looks like a 1. Okay? In those situations. Okay? And finally, the vertical stretch and compression. This is the number that's scooched right next to, but outside of the function. So it's multiplied, and then it's outside f at x. So it's going to be outside of the square root. It's going to be outside of the bracket squared. It's going to be outside of the absolute value function. Okay? So a function y equals f at x and y equals af at x are transformations of each other. Okay? If a is greater than 1, then it's going to be a vertical stretch. If a is a big number, vertical stretch by a factor of it. Okay? If a is going to be a small number between 0 and 1, like a fraction, like a half or a third or a tenth, then it's going to be a vertical compression It's still going to be by a factor of A. But of course, it's going to compress because you're halving the height, or thirding the height, or whatever it may be. You're thirding the y values. If A is negative, then the graph of y equals AF at x is a reflection. A vertical reflection in the x-axis. Okay? Now, we can also use this idea, okay, of transformations of functions. Now, we haven't quite got there yet. Okay, we really haven't got there yet because we don't even know what that K is. That's a new thing for us. But we're going to find these letters, okay, in these various locations. Okay, now usually we don't write linear equations in this format. Okay, but for a quadratic, the function is squared. Okay, squared. So as a result, the D is inside the function. The A is outside the function, the C is outside the function. The outside the function is vertical, inside the function is horizontal. Okay? For the square root, same idea. The function is a square root. So we look at the square root. Our A is out front and outside of. Our D is inside of and added or subtracted. And our C is added or subtracted on the outside of the square root function. Same thing for the absolute value because this defines the function. Again, we find A here on the outside. We find C on the outside, vertical on the outside, and then horizontal added or subtracted inside. Last but not least, the reciprocal function is the fact that it's over x or over a value. So again, inside the function, we find the D in the denominator. We find the A multiplied by it. When you have an A outside here, you just multiply the numerator by it, so you see the A over top. Okay, on the outside, see the function's down at the bottom, right? The bottoming, the dividing by that number is a reciprocal. And so really the A is on the outside, so it's on the outside of it, and of course C is also on the outside. So D, horizontal stuff inside, and plus C, vertical stuff translating, and A, vertical stretching. Okay? Now we're going to come back to this and understand it a little bit better, okay? And I will explain this technique for mapping rules and how they work for you guys later on, okay? Here's a little bit of a practice session to do. Okay, we want to match each equation below with the graphs to the right. So you'll see that they're all like root functions of some sort. Some are upside down, some are right side up, okay? So first of all, the easiest one, I think, if you look at it, is that all of them are right side up, right? The normal root function looks like this. Like that. Okay, that's what a normal root function looks like. Okay? The most obvious one is the one that's upside down. That one there. Okay? That one there should be pretty obvious to you. Okay? Because you got to look and say, okay, the A value has got to be negative. So I look for the only one that's got a negative A value. And in this case, the only one with a negative A value, to make it upside down, okay, is this one. So I go ahead and this one I make it B. Okay, that's for this guy here. Okay? The rest of them are right side up. And the rest of them are positive, 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 positive. So that doesn't really help me. Okay? So what I do is I start looking at the numbers. Okay, first of all, when I shift everything up and down, okay, and I look at the up and down, when I shift everything up and down, this guy isn't shifted at all. This guy is shifted down 3. This guy is shifted up 3. This guy is shifted down 3. So the only if we look at the original function, the red one, there's only 2 that are down 3. See how they're down 3 down here? Okay, so this one and this one are one of these two. So then I have to look at those two and decide. Both of these guys have gone down 3 from the original function, y is equal to root x. Oops, I should probably make that y is equal to root x. Okay, so to shift down from y is equal to root x, it's going to be this guy or this guy. So now I got to figure out who is who, because they are pretty much the same. One's x plus 3, one's x plus 2. So this means I'm going to shift, remember it's a plus 3, so my d value here is going to be minus 3. Here my d value is going to be minus 2. So that means this guy is going to shift to the left 3. This guy is going to shift to the left 2. Okay? So we've already gone down 3, and then we go to the left 2. That's this guy. When we go down 3 and to the left 3, that's going to be this one. Okay, so this function here is going to be the one that's got a d of minus 3 and a c of minus 3. Okay, so that's going to be number C. Okay, I don't have a lot of room to label them by their actual equations. And so by process of elimination, when the d is equal to -2, we've got a down 3 and to the left 2. Those down 3 to the left 2. That one is going to be equation D. Oh, sorry, equation E. The bottom. It'll look like an E. Okay, equation E. Okay, so now we've got C and we've got E. That's a +3. Then there's no +3 at all. Okay, so this one has got a D value of -4, which means it's been shifted to the left 4, but it hasn't been shifted up and down. So there's my basic function, shifted to the left 1, 2, 3, 4, but hasn't been shifted up and down. Well, that one is going to be A. Okay, which means, and we just got to make sure that's right, the only one that we have left, okay, is question D. That means it's going to be shifted up 3, and my D value is actually a +3. Okay, so we can move it out, we change the sign. So it's going to move 3 to the right. So does this move 3 to the right and move 3 up? 1, 2, 3 to the right, 1, 2, 3, yeah, it's not the greatest, it should go right to there. But yeah, that's going to be the final one that we haven't figured out yet. And that's a good question for matching, because you're really comparing and contrasting a lot of features. The only thing you haven't done is stretches, but you did do a reflection in here. So let's look at these ones. Sketch the following graphs by hand. State the domain and the range for each. Okay? And these ones are ones that we need to have a little bit of practice with. I like to start by sketching the base function and then from the parent function and then going from there. Okay? So I'm going to go ahead. Maybe I'll use a different color. All right, and I'm going to draw my XY axis, which I need to do, of course. Okay, XY axis, there we go. Okay, and then I start with my parent function. Okay, now you have to get to know these points really well, but the good ones to graph are 1, 1, and -1, -1, and then you go down towards it and back up, and then you go towards it and back up. Okay, so there's your base function there. You should draw in some asymptotes. Oh darn, I probably should have done that with a different color. Yeah, should have done it with a different color. There we go. Okay, so again, for your basic function, 1, 1, -1, -1, and you know how it approaches the asymptote, approaches the asymptote, approaches the asymptote, approaches the asymptote. And we got that piecewise function. Now, I've got a -2. That means it's going to be a D or a C. So I have to ask myself, is this going to be a D, a C, or is it going to be an A? Well, I know it's not an A because it doesn't multiply, and there's no number up top here to make this an A. Okay? With the D or the C, the D is always inside the function. So is this inside the function? Well, remember, the reciprocal function, y is equal to 1 over x. That's the parent function. The reciprocal function is all about being under something. And so the D is going to be inside and under. So this is a D value of +2. My C value will be hanging out here. Is there anybody hanging out there? No, there's nobody. Okay? So I'm going to sketch this guy in blue. Okay? I'm going to sketch this guy in blue. Okay? Oops, I forgot to put my asymptote. I should put my asymptotes in here. That's kind of an expectation when you draw a reciprocal function and label them. So y equals 0, x equals 0 in red. Now when I draw my function here, what I'm going to do is I'm going to shift, and I'm going to shift everybody to the left 2. Oh, sorry, to the right 2. So this is going to go 1, 2 here, and this is going to go 1, 2 here. And my asymptote goes 1, 2. So my dotted line goes from red to blue. That shifts over 2. Okay? Now there's no vertical shift, so nothing really happens to my other asymptote, but this is going to be x is equal to 2 and y is equal to 0. Strangely enough, D and C, D is x is equal to 2, C is y is equal to 0, because D and C define what your asymptotes are. So now you know what you can approach here and up here, and now you know what you can approach here and down there. Now it's a little bit tough, that one, okay? But my final function is in blue, and if you notice it carefully, you'll see that this red has shifted to the right 2, this red is shifted to the right 2, this asymptote is shifted to the right 2, but yet this asymptote stays the same because it hasn't moved up or down. Okay? To look at this guy here, there's a little bit more going on with this one. Okay? I'm still going to sketch my parent function, so I'll do that. I'll draw my xy axis again. Okay? I'll assume one square is equal to 1, rather than having to gum things up with labels and stuff like that. So I'll draw my parent function. A lot of people like to draw the asymptotes first, because then that kind of really tells you where you're going. One to the right, top right, bottom left, and then you draw your parent function. Your parent function. Okay? And there we have it. All right, now what we want to do is we want to figure out what the transform function is. I'll do this one in green. Okay, so in this case, inside the function down there is going to be my d value. So my d value is, switch the sign, -2. Notice out here we've got something outside of the function, but it's also added or subtracted. That's going to be my c value of 3. Okay? Now from there, what do? It's pretty simple, right? We take the asymptotes. Oh, I don't want to use green. I'm going to do that in blue again, because I used green for my axes. I don't want to do that. Okay, so what we're going to do is we're going to take our asymptote and every other value. So this value here, we're going to go 2 to the left and then up 1, 2, 3. So 2 to the left, 1, 2, 3. This one goes 2 to the left, 1, 2, 3. And those are my values there. Difficult for you to see that function from those 2 dots. So what you want to do is you want to take this asymptote and move it to the left 2. So that goes 2. Okay? That's to the left 2, right? And then this asymptote, it's not going to make it go up or down because it's an infinite up or down. But this asymptote is then got to go up 3. So then I go, this asymptote, I take it up 1, 2, 3, and then I draw the line. So 3 units up, 2 units to the right, and then I have something that I can approach.
Hi, Rick, or
okay? And so that's again this function here. All right, so it's a little bit tough with those translations, but you know, it is what it is. Okay, so a little bit of a foray into that stuff. Okay, now we're going to stop here because this is actually our next lesson, so we'll do this one separately. This is going to be horizontal stretches and compressions, which we haven't done yet. We didn't do it for parabola because the parabola was symmetrical, and vertical stretches look like horizontal compressions. And we factored out the a value, which is actually an a and a k value together, and blah, blah, blah. I'll talk to you a bit about that tomorrow. Okay?